Hello and welcome to this last part of the module Quantum Mechanics. In previous lectures, we understood the Schrodinger wave equation. From the time-dependent Schrodinger equation, we derived time-independent Schrodinger equation. We tried understanding the meaning of wave equation and the function psi here. We also understood the meaning of psi in terms of probability distribution function, particularly a probability of finding an electron, which is represented by psi star psi or the mod of psi square. We also understood the boundary conditions involved in terms of solving Schrodinger wave equation and the other conditions which are imposed when you have to solve the Schrodinger wave equation. Then from there we looked into the expectation values, the operators, which were particularly the energy and the momentum and the position operators. And then in the last lecture we tried using Schrodinger wave equation in kind of realistic scenarios, real world scenarios, and tried understanding the behavior of the particle, in this case behavior of the electron, in those particular scenarios. So the four scenarios that we studied was particle in free space. The second scenario we studied was the particle confined in the infinite potential well. So where the particle was confined inside the infinite potential well, so the potential inside the well would be 0 and the potential outside the well would be infinite. So the particle is trapped and particle cannot move outside. In this case we saw that there are clear distinct energy states, there are clear distinct states being formed as the solution of the Schrodinger wave equation. Each state has a distinct energy level and a unique psi function. Now this psi function represents the probability density function of the electron, and in all the cases we saw the probability of finding the electron was maximum at the center, whereas the momentum, the expected momentum, was close to 0. So depending on at which energy level or in which state the particle is, the probability distribution function of the particle in that particular state would vary. So we understood that the probability density function is a strong function of the state that we are dealing with, the energy level that we are dealing with, and the nature of the particle or the way particle may be present in a given confined space would also vary depending on the state that we are dealing with or the energy level that we are dealing with. The other practical problem that we looked into was the problem of a finite potential barrier, where the electron is tend to move or has a finite energy level, but this energy is lower than the potential barrier of the barrier or the tunnel barrier which is imposed in between. So this is the tunnel barrier, and what we found that in this case there is a finite probability for the electron to tunnel through this barrier. So the wave function would be oscillatory in this region, would be exponentially decaying in the second region, and again it will be oscillatory like the particle in free space in the third region. However, the psi amplitude, which translate into the probability amplitude, would decay, would reduce as the particle move from region 1 to region 3, which shows that while the particle has tunneled from region 1 to region 3, the tunneling is not 100% and the tunneling probability is less than 1. So as you see, the tunneling probability, we derived a relation for tunneling probability last time, and we found that the tunneling probability is a strong function of the barrier width, which is the parameter A here, and the potential barrier height or the barrier height of the potential. Higher the barrier height of the or the potential of the barrier height, or higher the height of this potential barrier, lower the tunneling probability, and higher the energy of the particle, higher the tunneling probability. So as I said, in this case the particle was found to behave like a particle in free space in these two regions, and the function was exponentially decaying in region number 2. This was interesting because conventionally or classically we are not used to of things tunneling through the barrier, but quantum mechanically, as we see, when the barriers are much thinner and when we deal with subatomic or atomic scale particles, there is a finite probability of tunneling. If you translate this into real world, in the classical world, you will find that there is still a finite probability of tunneling, but that probability will be so small that in reality we don't observe any physical tunneling. The fourth case we looked into was the case where the particle scatters through a potential barrier. Now in this case, as you see, the potential extends towards or the barrier extends towards infinity, and therefore in this case what we had found that the particle though tunnels or penetrates in this case inside the barrier, but it rebounces and comes back, but there is a finite penetration depth that we found, that we discovered last time, but eventually all the particles will come back and the reflection probability will always be 1, though there is some penetration into it, and the penetration depth, the penetration probability will reduce as the penetration depth increases. So the particle will behave like a free space particle in region number 1 in this case, and therefore the wave function was oscillatory in nature, whereas in region number 2 it should decay as it goes deeper and deeper in the barrier. Therefore psi 2 was an exponentially decaying function, where k2 is a function of the k2, which defines how fast it decays, is a function of the difference between the potential barrier and the energy of the particle, and rest are the constants like the electron mass or the mass of the particle, and h bar, which is the Planck constant divided by 2 pi, is also a constant. So with this recap, let's move on and let's look into a couple of numerical problems before we try to use the Schrodinger wave equation for few more practical scenarios. So the first question is, you have to calculate the penetration depth of a particle which is impinging on a potential barrier. That's the same case as we just reviewed. What you have to consider is that the incident electron is traveling with the velocity 10 to the power 5 meter per second in region number 1. So we had this case, this was the barrier, this is V naught, this is E, which is the energy of the particle, and so this is region number 1, this is region number 2, and in this case energy, which is nothing but half mv square, and V is given as 10 to the power 5 meter per second. Now assume that the barrier is at x equals to 0, so this point is set to be x equals to 0, and you have to find the total energy of the incident. You have to assume that the potential barrier, which is V naught, is 2 times E. So E is the energy of the particle, and V naught, which is the potential barrier height, is 2 times E. So first we calculate E. As you know, E is half mv square, so you feed the values and you get the value for E. So once we have value of E, we know what is V naught, and we just saw that psi is an exponentially decaying function in region number 2, and that was given as a constant times, please ignore this, constant times e to the power minus k2 x, and we also saw that k2 depends on the under root of the difference between the potential barrier height and the energy of the particle. Now it says that assume that the particle has penetrated, or you have to calculate the penetration depth. Now again it varies depending on what you consider as penetration depth. you can consider penetration depth as the point where this has decayed down to let's say 2/3 or close to 2/3. You can also consider this as the point where it has decayed all the way to 99% or greater than 99%. In this case, let's say if you take this as 2/3, or which would be close to e to the power minus 1. So we can say that for this function to become e to the power minus 1, the k2 times d, when we feed x equals to d, k2 times d equals to 1. So that's what we do here. K2 times d equals to 1. We know k2, we have to calculate d, and we equate that with 1. So if you feed all the values here, you get d, which is of the order of a nanometer. Now if it was 99% to this point, you had kept, rather keeping 1, you should have kept this as 5, and in that case this number would have been somewhere close to 60 angstroms or 6 nanometers. Let's see the next problem. So in this case, you have to calculate the probability of an electron tunneling through the potential barrier. So this is the other scenario where you have a potential barrier, and the width given is 3 angstroms. The potential barrier, this given, is 20 electron volt, and the particle which is moving has energy of 2 electron volt. Now we have to calculate the tunneling probability. We know the tunneling probability. This is something which we saw earlier, and we also know this function k2, which is a function of the difference between the potential barrier height and the energy of the particle times a certain constant. So you calculate k2 and you feed k2 back into this. In this one we have E, we have V naught, and we get k2 from this relation, and we have A, which is this barrier width. So if you calculate all of this, the tunneling probability turns out to be of the order of 10 to the power minus 6. So you can think in this way, that if you bombard 1 divided by 3.17 into 10 to the power minus 6 electrons, 1 electron will certainly tunnel. So out of these many electrons, which would be of the order of 3 into 10 to the power 5, out of these many electrons, 1 electron will certainly tunnel. Okay. So far we have seen several one-dimensional potential energy functions, and we solved the Schrodinger's time independent wave equation to obtain the probability function for finding a particle at various positions. Now you consider one electron or let's say a hydrogen atom like potential function, and we will see briefly that, considering the mathematical details of a hydrogen atom like system where you have one nucleus or a proton and one electron, what kind of potential function it will give rise to, and what kind of wave function or wave function solution that potential function will translate into. You will see that the results are very interesting and important. So if you assume one proton and one electron system, the potential built because of this particular charge configuration, very well, is Q1 Q2 divided by 4 pi epsilon r, Here epsilon we consider as, for the time being, consider as free space. It can also be something else. It can depend on the crystal that we are dealing with. The r is the spacing between the proton and the electron, which for the time being can say we don't know. And E, the E is basically the charge. So across proton you have E and electron you have minus E. So this becomes minus E square, and this results into a potential distribution of this kind. As you can see that the potential function is spherically symmetric, and therefore it leads to a 3D problem. And in this case you have to basically solve a 3D Schrodinger equation, which is of this form in 3-dimensional or spherical coordinate function with r, theta and phi. So now you have to solve this this Schrodinger equation in the spherical coordinate, and to solve this you apply, as you know, separation of variables for r, theta and phi. So as you know that the del square term here is the Laplacian operator, and you know that it has to be written in a spherical coordinate, and then this entire Schrodinger wave equation will be translated into spherical coordinate. As I said that you have to then apply separation of variables. So if you apply separation of variables, your time independent Schrodinger wave equation, assuming that r, theta, phi can be separated, time independent Schrodinger wave equation can be written as psi r times psi theta times psi phi. You can also write these as different function as r and psi and phi for simplicity. In this one you will note that the second term in the equation is a function of just the psi only. If I elaborate this this Laplacian operator, this is what you will notice, and therefore you will notice that the second term can be written directly in form of psi, and the solution of this would be of something of this kind. Here m is the separation of variable constant. Similarly, since the wave function must be single valued, we impose the condition that m is an integer, and therefore you set m equals to 0, plus minus 1, plus minus 2 and so on up to plus minus L. Here L is another quantum number, and L is such that n is greater than equals to L. N is the principal quantum number, and this n is what defines the energy level or the state of the system on these levels of the system. So the energy of the particle can be defined by this relation, and this energy is directly related to or inversely proportional to the square of n, where n is the principal quantum number. Now if we, so from where these quantum numbers came, if we again go back to the Schrodinger wave equation and incorporate the separation of variable constant, we can further separate the variables theta and r and generate two additional separation of variable constant L and M. So far we looked into phi, and if we divide this further, if we separate this further, we can separate it further for r and theta, and if we solve it, we get this additional separation of variable constant L and N. So therefore we ended up getting these three separation of variable constant N, L and M, which are also known as quantum numbers. As I mentioned that the parameter N is the principal quantum number, L is the azimuthal or angular quantum number, and m is the magnetic quantum number, which most of you have seen in your standard 12th textbooks. So the relation is starting with the principal quantum number, n starts with 1, 2, 3 and so on. L starts with 0, and L is basically 0 up to n minus 1. So it will have all, let's say if n equals to 3, then L equals to 0, 1, 2. M is basically, as I said, 0 plus minus 1 plus minus 2 all the way up to plus minus L. It can also be written as that M mod is equals to L minus 1 and so on up to 0. And finally, if you solve this Schrodinger equation, as I mentioned, you get the relation for the particle energy or the electron energy, and the electron energy is inversely proportional to n square, which means as you go to higher and higher orbitals, higher and higher n values, the energy of the particle will reduce. But as you notice that the energy is always negative, which means the particle is bound to the nucleus, and for the energy to become positive, the particle need to leave the nucleus. So till the particle is bound to the nucleus, no matter how many shells, in what shell it is, whether it is in first shell or second shell or third shell and so on, the particle is always bound, the energy is always negative. However, as you move away from the nucleus, the particle energy will reduce, which means that the probability of knocking off the electron from the orbital will reduce with increasing L. So now let's look into a numerical problem, and let's try to calculate the energy level of an electron in a 1 electron atom. So what we try to do, we try to calculate the first 3 energy levels, which means we are going to calculate energy for n equals to 1, 2 and 3, right? So we have the formula that we saw in the previous slide. This formula you get by deriving the solution of the Schrodinger wave equation in this spherical coordinate for 1 electron system, where you have 1 electron and 1 nucleus present. The similar calculation of energy we have seen in the past for those 1-dimensional problems. Since this is a 3-dimensional problem, we can't solve this using pen paper, but if you look into a detailed derivation of this 3-dimensional Schrodinger equation, you will get this energy function. As I discussed in the previous slide, the energy function is inversely proportional to n square, where n is the principal quantum number. So let's start feeding values. Here everything else is going to be same. All we have to do is we have to change this value of n from 1 to 3. So if you feed all the values, you get minus 13.58 divided by n square electron volt. This is something that you can remember and will come handy when it comes to calculating the energy level of particle in a given shell. So here n is the shell number, n equals to 1 will be shell number 1, 2 shell number 2 and 3 is shell number 3, and as you feed the values you realize that the energy of the first shell is minus 13.58 electron volt, the second is minus 3.39 electron volt, and the third is minus 1.51 electron volt. Now keep in mind that this is for free space, because we kept the free space mass of the electron and also the epsilon of the free space. Now if you change the permittivity of the material, this value from epsilon r, if you make it epsilon not epsilon r, where epsilon r is the permittivity of any given material in which you are treating the particle, these numbers will change. So for instance, if you change from free space if you replace with some material, let's say you make it 11.7, which is for silicon, the values will be very different. The values that you get for the first level is 99.2 electron volt, and it goes all the way down to minus 11 milli electron volt. So as you see, the numbers drifted from electron volt to milli electron volt as you increase the permittivity values. Okay, so now if we can analyze few things further. That is what you studied in class 12th earlier. So you studied periodic table, and you also studied these quantum numbers. Now as you see that these quantum numbers are derived from Schrodinger wave equation, or they are basically these constants which come out as the solution of the Schrodinger wave equation, which gives you these values for different values of n, L and M. And as you progress, for instance, when n equals to 1, you have L equals to 0 and M equals to 0. Again, there are two possibilities, and I'll tell you why. For the same n equals to 1, you have two different possibilities, two different states in this case, and there you fill 1s1 and 1s2, and the first one is for the hydrogen atom, and the second one where you have 2 electrons possible is for the helium atom. We also remember that the solution of the Schrodinger equation must be unique, distinct or single valued. We also know that though the electron has a finite angular momentum, the overall system must have zero momentum, and therefore if one electron has a certain spin, the other electron must have the opposite spin or the opposite angular momentum, which basically translates into the opposite spin. And therefore with each wave function that you calculate, you get 2 electrons. One corresponds to the positive spin and the other corresponds to the negative spin. And to keep the amplitude aligned to what you get the solution, this spin is given as plus half and the minus half. So now we already had 3 quantum numbers, which was n, L and M, and we got one more quantum number, which is the spin quantum number, which is S. The second aspect, which again comes from the solution of Schrodinger equation, that for the 2 wave functions to be distinct, single valued, that means that no 2 electrons can stay in a given state or in a given quantum state. So if you have a given value of n, L, M and S, that will correspond to a unique quantum state, and this unique quantum state corresponds to a unique particle. So which means that you have unique quantum state corresponding to each electron. In other words, in a system you cannot have 2 electrons which occupy the same state or the same quantum state or the same quantum numbers or the same set of quantum numbers. And that's why you see for each electron that we deal with, the quantum number set would be very different, right? So if n, L, M are same, the spin value would be different, for example. Okay, so now if you solve this Schrodinger equation for one electron atom which has a proton and an electron with a spacing r, and you solve the Schrodinger equation, as I said, the Schrodinger equation will give you multiple solutions, and each solution will correspond to a unique n, L, M value, and for each n, L, M value you get plus half a spin and minus half a spin. As for the wave function is concerned, the wave function psi would be a function of L, M and n values, and for each of those psi l m n you will have two possibilities, which is psi s equals to plus 1 by 2 and psi s equals to minus 1 by 2. So now if you solve this, as we also did this earlier, we for instance when we solved this particle in a infinite potential barrier, we got multiple solutions, we got multiple states. Each solution was a unique state. So electron can be present in a state which was corresponding to energy E1, or it could be present in a state corresponding to energy E2, or a state corresponding to energy E3, and so on and so forth. Similarly, in this case, you get multiple solutions, and each solution corresponds to a unique state. Now each state will have a unique probability density function or unique psi value. So in this case, we have shown the r, theta, phi as separate functions. So the final wave function will be a product of all these three. So if you keep n equals to 1, l equals to 0, m equals to 0, what you get is a product of this, and this. Now you change n to 2, and for n equal to 2 you have the following possibilities. You can have l equals to 0, you can have l equals to 1, and for l equals to 1 you can have n equals to 0 and m equals to plus minus 1. So you get multiple possibilities for n equals to 2, and for each of those cases what do we get is we get a unique wave function. So the wave function will be a product of these three, which is, because of separation of variable, we have r, theta, phi. Okay, so as you can see here, now here we have shown the product. So for each unique value of n, l, m combination, you get a unique wave function. As you change the n, l, m values, you get unique wave function. Now each wave function corresponds to a unique state in which the particle can be present, in which the electron can be present. You know that the electron has the highest probability of the electron to be present in case of hydrogen atom is this, but the electron can be excited, and if the electron is excited and if it moves to the next state, it will follow a wave function as this. If it moves to another state, it will follow wave function as this, and so on. So depending on in which state the electron is present, it will follow that particular unique wave function. Classically, you can think in this way that it's the same particle, it's the same electron, but as it moves to different houses, the behavior of that electron, the probability where the electron can be present most of the time would be different. The behavior of the electron will different, the energy of the electron will different, the momentum of the electron will different, the expected position of the electron will be different, and that is dependent on the wave function corresponding to that particular state. So you can think of these different n, l, m values as addresses of unique houses. So you can think of these unique states as unique houses, but as it moves to different states or different houses corresponding to a given address, the behavior of the electron would vary, the behavior of the electron will change, and that behavior must follow the solution of the Schrodinger wave equation, which is the psi that I have listed here. Now let's see what does it mean. So let's try to analyze the solution of the Schrodinger wave equation in case of this single electron atom. For instance, when n was equals to 1, n was 0 and m was 0, the psi that you get is this. As you see that this is an exponential function and it decays exponentially, as you increase the distance as you go away from the nucleus. So r was the radius, and as you increase r, you actually go away from the nucleus. But you also see there is a parameter a naught, and this is inversely proportional to a naught. So if you plot this, if you plot the probability density function and normalize it with a naught, both the distance as well as the probability density function, what you get is a function like this. Normalizing by a naught means at r equals to a naught, the function is maximum, and that's when the probability is half. Now, as you know that this is spherically symmetric, so this is not a one-dimensional solution, this is spherically symmetric, so you have to visualize this in a spherically symmetric fashion. What does it mean is that you know that 1s orbital is spherical from the high school textbooks, but as you can see, this is not truly spherical, as in that inside a sphere the electron probability is 1 and outside a sphere it's 0. It exponentially decays. There's a point which is called the radius, at which the probability of finding the electron is maximum, and as you go below the radius, the probability of finding the electron decays, and as you approach towards the nucleus, the probability of finding the electron will be 0. And this is for n equals to 1, L equals to 0, and m equals to 0. As you go higher orbitals, let's say if you make n equals to 2, what you get is a function like this. And in this case, as you see that the maxima is somewhere around when r equals to 5 a naught. Right. So in this case, the maximum, the probability of finding the electron is highest far away from the nucleus, also far away from the first orbital or the region where the first orbital was present, and the function is smeared out rather in a larger volume, and therefore the probability of finding the particle at the maximum point is also on a lower side. Now this again is spherically symmetric, so if this is spherically symmetric, you know this will look something like a donut. So if you solve this further and find where the psi is maximum, you solve it for a naught. And you find that the psi is maximum when r equals to a naught, which is this value, and this value is same as what was given as by Bohr as Bohr's radius, which is 0.529 angstroms. Okay, so as I said, you have to visualize and see the 3D view of these orbitals. So if you plot them 3-dimensionally, this is what you see for the 1s orbital, but if you take a cross section, what you see as what I have shown, inside that if you take a cross section, you will notice that close to 0, which is the nucleus point, the wave function will go down to 0, and it will be a maxima at Bohr's radius, and it will again decay down to close to 0 as you move further. The other orbitals, the 2p orbital looks like a dumbbell, and that's why you see something like this here. Similarly, if it is the 3d orbital, as you can see, the 3d orbital waveform, wave function shape, or the probability density function for the electron would be different than what it is for the 2p orbital or what it is for the 1s orbital. So as I said earlier, that the behavior of the electron as it moves to higher and higher orbital, or as it moves to different orbitals would vary depending on the wave function assigned or the wave function associated with that particular orbital, which is corresponding to the quantum numbers associated to that particular orbital. Okay, so now let's see how do we apply whatever we have understood so far to solids. Now the situation with solid would be very different. I mean, so far we saw more simple one-dimensional problems. Then we applied all that understanding into something which was three-dimensional, but still we were dealing with one unique potential function which was produced because of an electron and a proton. You can imagine that the entire periodic table and the orbital theory that you see so far or you have studied so far is based on the Schrodinger equation or the solution of the Schrodinger equation for the hydrogen atom, which is just one proton and one electron system. If it was the solution of the Schrodinger equation of a heavier atom which has possibly a rather heavier nucleus and many more electrons, the solution would be a lot more complex because you have to deal with a lot more complex electron function or electron distribution, and therefore a lot more complex potential distribution across that particular atom. And of course the psi value will also be different. The behavior of electron at different energy levels will also be very different as you go to heavier atoms, and what we derive out of the hydrogen atom solution doesn't work really for those heavier atoms. And if you really want to do a solution for those heavier atoms, you have to solve Schrodinger equation for the actual nucleus with the amount of charge across that nucleus and the actual system around it, which is considering all the electrons around it, and therefore the kind of complex potential it will form, and then the solution will be a function of that particular potential, and it will of course look very different, very skewed from the solution that we have seen so far based on the hydrogen atom model. The textbooks will mostly have the hydrogen atom model based description of the atomic orbitals, but in reality these orbitals look, as I said, a lot more complex, and their interactions are also fairly complex. So that's why for solving these real systems with multiple atoms together and many electrons, you have to use things like or theories like density functional theory, which helps you simplifying all these solutions and get the probability distribution function across the entire system, and which helps you understanding how the electron will behave across a system having multiple atoms and so on. Now, talking about multiple atoms, solid is a unique example which we are going to deal with. But talking about solids, you can imagine that we may be dealing with systems having hundreds and thousands and possibly millions of atoms. If you're talking about bulk materials, bulk semiconductor or metal and so on, you are talking about millions and billions of atoms, and practically even with the biggest supercomputer possible, you cannot solve Schrodinger equation across such a system. So there you have to apply some simplification, and to understand what kind of simplification will be applied, we have to first understand how the wave function will behave in a solid. Now you can think of solid as a system where you have certain electrons bounded by an atom. However, there are many atoms which you have now moved closer. As you saw in the previous slide, the calculation tells us that the Bohr's radius was of the order of half an angstrom, and if you go to higher energy orbitals like the 2s orbital and the d orbital and so on, the radius or the spacing of the electron from the nucleus was of the order of several angstroms. Now the moment you get into several angstroms, which means the wave function exists in those in that several angstrom region. And if you talk about solids, let's say you talk about silicon, which will have a 1s orbital, a 2s orbital, and a 2p orbital, which means that the wave function of the outermost electrons which are present in the 2p orbital, that wave function will be present far away from the nucleus and certainly several angstroms or maybe close to a nanometer away from the nucleus. Now the interatomic spacing in these solids, let's say if we talk about silicon, would be order of few angstroms, which means that these wave functions are going to overlap over each other, right? You have one atom which has a wave function of certain orbitals positioned few angstroms away from the center of the atom or from the nucleus. You have another atom which has a wave function of outermost electron present few angstroms away from the nucleus, and when you bring these two atoms closer, when you bring them closer to a spacing which is of the order of this distance of these wave functions, then the wave functions will overlap, right? And you remember that the wave function is nothing but the probability density function of the electron, and if there are two wave functions which are overlapping, the electrons will be interacting with each other. We also know that no two electrons can be present in the same state, and the solution of the Schrodinger equation must also be distinct, which means that these wave functions will try to do something because of their interaction, and they will try to basically change the wave function further. That's what we are going to see now. We have to keep the Pauli exclusion principle in mind all the time, and as I said, we have to keep in mind that so far whatever we did, that was basically electron was bounded with an atom within a free space. There was nothing around it which can interfere with it, and therefore we have seen all discrete values of energies, and the energies were all quantized. Now energy levels are fixed, or energy range is fixed. So if some new energy levels are created, that energy levels will be created in between the existing energy levels. That's also something that you can visualize. So keeping all these in mind, let's try to generalize our understanding for a crystal lattice. So as I said, that you have, let's say you have one atom which is present here, and the atom has a wave function which looks something like this, which is the maximum, the probability of finding the particle is maximum at a distance a naught. Let's say this point corresponds to the nucleus, so this is somewhere at a naught, and the wave function will continue to be present at distances close to 5, 6 a naught or even greater, right? It can be anything, depending on the wave function that we are dealing with. And then I said that let's assume that you are bringing another atom. So you had one atom here, you had one atom here, now you are bringing it closer. So initially this has a wave function like this, this has a wave function like this, and now you are bringing them closer. So it translates to something like this, where there is a region where the wave functions are overlapping, the wave functions are interfering with each other. Now you also know that there was a distinct energy level associated with this psi, and the energy associated with this, let's say if it was En, and if this was also En, we know that when this was not the case, then En, this side was equals to En. Now we also know that from Pauli exclusion principle, we cannot have the two electrons occupying the same quantum state and therefore the same energy level. So the energy levels must split. The this region, the wave function, the psi, must also change, and that's what it happens here. So as you can see that that you had a certain energy state, certain energy level, and that got splitted into two distinct energy states. Now if you have, now this is the case when you have two atoms which you have brought closer to each other. Now imagine that you have millions of atoms and you are bringing all those millions of atoms closer to each other. What will happen to this energy state? Let's see that further. So if you are bringing more and more atoms further, so you started with one energy state when these atoms were far apart. Let's say these atoms were far apart. Now you try to bring them closer, you reduce this gap, and as a result of that, their respective wave functions will overlap, they will interfere with each other. The Pauli exclusion principle will not allow the particles to be present in the same energy state, same quantum state, and therefore these energy states will split. I mean, this is just a representative picture of the energy splitting. The energy splitting happens in different ways. The energy may increase and the energy may fall. One is basically the anti-bonding, which gives rise to the potential energy of the particle, and the other is the bonding, which is because of the repulsive force between the nucleus, and it basically lowers the potential energy of the particle. Now imagine that if you have energy spacing of 1 electron volt for two different energy levels. Let's say this is E1 and E2, and this was for 1 electron with an energy spacing of 1 electron volt for two different energy states. And now you bring, let's say, 10 to the power 19 electrons closer because of 10 to the power 19 atoms being packed into a solid. Now what will happen? All these energy states which were discrete and distinct earlier and unique, now they all will split, and within this gap you will be creating 10 to the power 19 levels, which means the gap between each level will be 10 to the power minus 19 electron volts. And this is the situation when you say that the energy continuum, or the what you call band, is continuous. It's not continuous, it's still discrete, but the gap is so small that you see it as a continuous level. Okay, now what will happen if it is silicon? In silicon, let's put this whole thing in case of silicon. In silicon you have you at n equals to 1 you have 2 electrons. For n equals to 2 you have 8 electrons. N equals to 2 you have 2s and 2p. So which means we are talking about three different energy levels. We are talking about n equals to 1, n equals to 2, and n equals to 3. This is 1s, this is 2s, and this is 2p. Now with each energy state, when you pack these atoms closer and closer, each energy level is going to see a split. So all of them will split into a smaller or into a larger band, and in reality basically they will split in a way that, for instance, the innermost electrons which is associated with n equals to 1, they won't contribute in anything as far as the valence electron is concerned, but the outermost electrons, which is basically initially you have 2n electrons which are present in the 3s orbital, and then you have 2 electrons which are present in the 3p orbital. The energy states will split, and because of the anti-bonding and bonding orbital formation, you create a band gap. So, and then what you call on the higher side is the conduction band, which will have 4 states present, 4 states being vacant and 0 electron being present there, and the bottom portion is what you call as the valence band, and in this case you have 4 electrons per atom present, 4 states per atom present, and 4 electrons occupying those 4 states. So the valence band, that's why, is completely occupied, because all its states are occupied, and the conduction band is completely empty because all its states are empty. So initially, as you know, that we had this gap, and the gap was 3s and 3p gap. In 3s you had 2 electrons, and in 3p you had 2 electrons, and as they start interacting and as the energy splitting happened, a band was formed, and all the electrons which were present in the 3p orbital moved to the what is called as the valence band, and all the states were occupied, and the other band, which was the conduction band, which is the higher energy orbital or higher energy band, became all empty. So this happened because of the splitting of the 3s and the 3p orbitals, and as I mentioned that it also formed a forbidden energy band. So we always had a forbidden energy gap. I mean, when you had these discrete energy levels, this region or this region is the forbidden gap. I mean, you cannot have an electron present in that region. Similarly, we have got a forbidden gap, so you cannot have a state, you cannot have an electron present in this particular region, and the electron can be present in either these energy levels which are continuous, or these energy levels which are also continuous. Okay, so now the question is that, so far we tried to understand how the bands are formed, how the orbitals interact when you form a solid, and how these energy states look different when you form a solid, and what is the difference between the whole orbital picture in case of a solid versus the whole orbital picture in case of an individual atom. And many of these things that we borrow from our understanding from an individual atom, and what kind of understanding we can extrapolate, and what else we have to basically derive based on the other fundamental facts and understandings like Pauli exclusion principle and the distinctness of the wave equation and the interaction of the wave equation and so on and so forth. Now let's see how we can if we can derive or if we can solve a Schrodinger equation for solid. Now to do that, what is often used is the Kronig-Penney model. The Kronig-Penney model basically try to simplify a lattice system, and this is just a model to understand how things may be. If you want to extract band structure, the procedure is rather complex and you have to do a 3-dimensional solution for that, but here we are going to simplify to a 1-dimensional lattice. So we can start with a single atom. You know that the single atom potential distribution function will look something like this. In this case, when I say single atom, means the atoms are not interacting. I mean, even if there is an atom in the surrounding, they are not interacting yet. The potential function that we saw earlier was basically inversely proportional to the radius and directly proportional to the charge square, and we also saw these distinct energy states being created, and as you go to higher and higher energy levels, you get to the ground state, and the moment your energy is higher than the ground state, the electron is not any way bounded with the nucleus, but till it's bounded, the energy is lower than 0 electron volt. Now if I bring more and more such atoms closer to each other, the potential function will interact in these regions. So it can be simplified further into something like this, where you have these atoms being present here, and the potential around the atom would look like a periodic function of this kind, which can be further simplified into something of this kind. So you have got these two regions, region number 1 where you can assume there was no potential, and region number 2 where you can assume there was a finite potential. So here we have lifted everything up. I mean, earlier we were dealing with things from minus infinity to a value 0. Now we have lifted it up. So now we are dealing with some finite value, or let's say 0 value to some finite value. So we can solve Schrodinger equation for this kind of potential function and draw some conclusion out of it in terms of how the particle will behave, how the electron will behave inside a solid having a periodic potential distribution across the lattice. So if you consider 1-dimensional lattice, you get this 1-dimensional periodic potential function. what we apply the Kronig-Penney model. The Kronig-Penney model is nothing but it starts with the Bloch theorem that the solution of the wave function for periodically varying potential must be of this form. So we use this form of the Schrodinger equation or Schrodinger equation solution or psi value, and we'll try to find conditions for which this form is valid. So use this to solve the Schrodinger equation, and you have to solve for both region 1 and 2 as we have often done earlier. You apply the boundary conditions and you satisfy the condition for which you get this form of the Schrodinger equation. We will not get into the solution of the Schrodinger equation here, but I will quickly jump to the condition for which the solution satisfies or solution gives you this particular form. The condition is this, where the P dash is proportional to the mass of the electron, the potential which is this value here, and the parameters B and A, which are basically nothing but the width of the potential barrier and the gap between the two atoms. So A, you can think of A as the interatomic spacing, and you can think of B as the region till which the potential influence of the potential can be experienced. V naught, as I said, is the potential experienced by the potential, the additional potential experienced by the electron present, let's say in the valence shell. So if the electron is present in the valence shell, and if that electron experiences a potential, let's say minus V, and we are referring from the ground state, so the height that it experiences is V. So this height or this additional potential that the electron must surpass to leave the atom is this potential V naught here. H bar, you know very well, is the Planck constant or the reduced Planck constant. Similarly, alpha is related to the momentum of the particle. So alpha is nothing but under root of 2me divided by h bar square, or alpha square is 2me divided by h bar square, and A is the interatomic spacing between the two atoms. Here K is the momentum of the particle. So we have seen K earlier, that the K is related to the momentum of the particle, as we will also see in the next slide. So what we will try to do, we will try to, so we have in this relation, we have energy, we have K or the momentum, and rest everything else are certain constants. So what we will do, we will try to, if you plot this function, if you plot the solution of this function, you get a relation, or you get a relation between energy and the momentum, and that relation between energy and the momentum is actually called the band structure of that particular crystal lattice, and that band structure tells that how the electron is going to behave in that particular lattice as far as the energy and the momentum relation of that particle is concerned. The band structure will also tell you the gap between the valence band and the conduction band, as we will see in the next slide. Now before that, if you want to check whether what it translates into, let's say if V not equals to 0, which means that, as I told you earlier, that the delta V, which was the height between the energy of the electron in the outermost shell versus the ground state, if that becomes 0, which means the particle is now a free particle, and if you make the particle free particle, we can see what kind of energy momentum relation we get here. So you can feed all these values here. In this case, the P will become 0, the cos alpha A will become cos Ka, which means alpha equals to K, and as we have seen that in the previous slide, that alpha square equals to 2me by h bar square. This translates into k equals to under root of 2me divided by h bar square, as I also told you in the previous slide that alpha is related to the momentum of the particle, and if you further simplify this, k becomes p by h bar. So as I said, k is nothing but k is related to the momentum of the particle, and when you use parameter k is basically reduced momentum or momentum divided by h bar. So you can also think in this way that the h bar k is also called the crystal momentum, whereas the p is used for the particle momentum. So that's the relation between the crystal momentum and the particle momentum, and when we use k we are talking about the crystal momentum. So now if you plot this relation, which is k equals to p by h bar, or if you plot this relation, which is relation between energy and the momentum, what you get is a parabola, as you can see here, and this is something which we saw earlier as well, which was the relation between energy and the momentum for particle in free space. So when you solve this, the Kronig-Penney model for particle which is bound in a crystal lattice, but the moment you set conditions in such a way that the particle behaves like a free particle, or particle is experiencing zero potential, which means particle should behave like a free particle, the energy momentum relation reduces to the same relation as we have seen for particle in free space. Now we will see what happens if you don't relax the potential. If the potential is finite, which means the particle is still bound within the crystal lattice, if that happens, you basically plot basically the relation between k and alpha, or various possibilities of energy and the momentum for meeting the solution of the equation that we saw in the previous slide. What you get is something of this kind, and you can think of this as different bands, different energy bands. And if I simplify this, it appears to be something like this, which is called the reduced k space. So we are plotting k between minus pi by a to pi by a is the interatomic spacing, and this is your conduction band, and this is your valence band. What you have often seen in the undergraduate textbooks, you often talk about the band gap, which is this gap, and this band gap is measured. This is what you are used to of, and this band gap is measured when the momentum is 0, when the k value is 0. Now what does it mean? It means that that as the particle energy increases in the crystal lattice, the momentum of the particle will also increase, or in other words, as the momentum or the velocity of the particle in crystal lattice increases, the energy of the particle will also increase. And as we will see later that there are various aspects of the particle that we can derive out of this band structure. Okay, so let's stop here, and this basically ends the module quantum mechanics. So far we have understood the Schrodinger wave equation, and we have applied Schrodinger wave equation all the way from simple one-dimensional problems to a system which is one electron system like a hydrogen atom, and then we have tried to get a qualitative feel for what happens if you solve the Schrodinger wave equation in a crystal lattice, and then how the because of the quantum mechanical rules, how the behavior of the particle will change when it is bound within a crystal lattice, and then what kind of conclusions we can draw because of the interaction of the wave function when the particle is bound inside a crystal structure or a crystal, and how it leads to energy splitting, how it leads to the formation of bands and the forbidden gap and so on, and therefore how it leads to formation of what we have seen is the band structure, which is nothing but a relation between the energy and the momentum of a particle inside a crystal lattice. And going forward, we will use this band structure to derive and understand the behavior of the particle inside a crystal lattice. And going forward, when we study the transport of the particle, the transport of electron in semiconductors, we'll also use this band structure and the understanding we developed so far in deriving the behavior of an electron inside a crystal lattice, deriving the properties like the saturation velocity, mass, and so on and so forth of electron inside the crystal lattice. And based on that, we'll further build into from the behavior of electron inside crystal lattice, will further build into the statistics of the electron, and then using that we'll also develop further understanding on the devices and device physics. So with this, thank you very much, and we stop here, and I'll see you in the next class.